Hello, my name is Yana author's pseudonym Butko, and I will tell you a little bit about Chernoff approximation of Markov processes. All what I will tell you and all that I will have no time to tell you, you can find in my survey paper, which has appeared in this year in Springer Proceedings in Mathematics and Statistics, and also it is available in arXiv. Well, so let us assume that we have a time homogeneous Markov process. This process does not have memory, and the most important thing about this process, which we have to know, is its transition kernel, which is a function p of tx dy, which describes the probability of transition from point x to the set dy when the process has t times units. So if we have a Markov process and its transition kernel, then we can define an integral operator with this transition kernel, or actually a family of operators with parameter t. And this family of operators happens to be a semigroup, operator semigroup. That is, this family satisfies these two conditions. It is an operator semigroup on a space of all bounded Borel functions. But it also, in some cases, it happens to be a strongly continuous semigroup on some smaller Banach space or on some other Banach space. In this case, one can find a derivative at small t equal to 0 of this mapping, and it is usually some unbounded operator L, so that the semigroup TT is actually something which plays the role of the exponential function of L. And this L is called generator of a strongly continuous semigroup TT, and also a generator of the process psi. Well, so we have started with the Markov process. We have its transition kernel. Then we can define its semigroup, and if it is a strongly continuous semigroup, then this semigroup, with the help of the semigroup, one can solve the evolution equation, the Cauchy problem for the following evolution equation. So on the left-hand side, we have derivative of with respect to time. The first derivative with respect to time of an unknown function f, and on the right-hand side, we have L applied to f, where L is this is the generator of a strongly continuous semigroup TT. So we have, roughly speaking, three equivalent problems. So on the language of stochastics, the problem is to find the transition kernel P of a given Markov process psi. On the language of functional analysis, this task can be interpreted as the task to construct a strongly continuous semigroup with a given generator L. And on the language of partial differential equations, the same task is to solve a given Cauchy problem for a given partial differential equation. And the problems in functional analysis approach and PDE's settings, they of course they have to be solved in some given Banach space. Okay, so a classical example is the heat equation. This is an evolution equation with operator L, which is just 1/2 Laplacian. The solution is given by the so-called heat semigroup. This is a family of integral operators with Gaussian kernel. It is a strongly continuous semigroup on many Banach spaces like LP spaces and a space of continuous functions vanishing at infinity. And these kernels, Gaussian kernels, they are nothing else but transition kernel of Brownian motion. But unfortunately, there are not that many examples of processes so that their semigroup or their transition kernels are known explicitly. And hence, it is not possible to find such a nice formula. And one has to construct some representations of a semigroup TT or some approximations of the semigroup TT. Of course, there are many different possibilities how to do that, and today we will discuss only one of them, the so-called Chernoff approximation. So there exists a theorem of Chernoff, which says that under some conditions, under some circumstances, a given family of operators f of t, this family is not a semigroup, but these operators are nice. They are known in the sense that they are given explicitly. So under some conditions which are given in the theorem of Chernoff, the following identity holds, namely that an unknown semi-group TT with a given generator can be approximated by this limit where we have iterations of some known operators F. Okay, this formula is called Chernoff approximation, and this formula can be interpreted in many different ways. For example, first of all, this formula immediately gives a discrete time approximation to the solution of the Cauchy problem for the corresponding evolution equation. So what we have a numerical scheme for the corresponding PDE in one hand. On the other hand, in some cases, one succeeds using this family F, one succeeds to construct a Markov chain approximation to the original process, Markov process Xi. Namely, one succeeds to construct a sequence of random variables such that the following condition expectations are given in terms of the family F, family of operators F, which are used in this Chernoff approximation formula. Then, using this identity and this identity, I can rewrite the Chernoff approximation in the following way. This is nothing else but just using this identity and Tower property of condition expectations. And what does it give us? In some cases, this Xi is a solution of a corresponding stochastic differential equation. And then this sequence sometimes corresponds to the Euler-Maruyama numerical scheme for this SDE, and hence this identity, which is nothing else but the Chernoff approximation. This is nothing else also but the weak convergence of this numerical scheme solving the SDE. So, okay, so if we have a Chernoff approximation of a strongly continuous semi-group of operators, we have simultaneously numerical scheme for the corresponding PDE. In some cases, we have also numerical scheme for the corresponding SDE. And in some cases, when then the semi-group is represented as some path integral, for example, like a Feynman-Katz formula, then the right-hand side is just a limit of iterated integrals, for example, or the limit of iterated operators which are known explicitly. So this formula gives us also approximation to path integrals in the Feynman-Katz formula. Okay, so there are three interpretations of what the Chernoff approximation can give us. Well, so in my research, I follow the so-called Lega principle for Chernoff approximation. What does it mean? It means that we start with some simple operator, simple generator, and hence simple Markov process. Simple means that we either know the transition kernel of this process, or we know already Chernoff approximation to the corresponding semi-group. Then we apply some operation on the process or respectively on the generator, and we obtain a new semi-group. And the question is how one can construct Chernoff approximation for the new semi-group if the Chernoff approximation for the old one, for the original one, is known. Assume that we are able to solve this problem for many different operations. Hence, we have a kind of Lega constructor at hand. Namely, we can start with something simple like Brownian motion, and then we apply many different operations one by one, and we construct the corresponding Chernoff approximations for the constructed semi-groups. At each step, we obtain some more and more complicated process, and we obtain respectively more and more advanced Chernoff approximation. Nowadays, so once again, it is nice to start with processes with known transition kernels. There are some of them, and they appear from time to time, some new of them. It is also nice to start with processes which are already Chernoff approximated. In this case, I would like to mention failure processes in RD and also failure diffusions in the Riemannian manifold. And here are some operations which we know how to deal with. Namely, we know how to construct the corresponding Chernoff approximations. Unfortunately, we don't have time to discuss them now. Here are some names related to the results. And you can find all the details about all these operations and all references in my survey paper, which I have already mentioned. And the last thing which I would like to say is that so on one hand, it is very nice to have Chernoff approximations for semigroups generated by Markov processes. On the other hand, operator semigroups are also building blocks for more advanced, for solutions of more advanced equations, like time fractional evolution equations or stochastic partial differential equations. So in some cases, the solutions are given by some formula which contains as an ingredient some strongly continuous operator semigroup. So if we know how to approximate this strongly continuous semigroup, we also know how to approximate the solution of this more advanced problem. So Chernoff approximation is an important thing which can be used in many different ways. And you are welcome to find more details in my survey paper, The Method of Chernoff Approximation. So thank you for your attention. Have a nice day. Bye.